Okay, in this video, I'm going to go through the problem set 2 solutions. So I've listed this, or I've posted this as a PDF, but this is going to go through with more of a verbal definition of these, okay? So the first one is in section 2.1, problem 2a. So we're going to consider the definition-based algorithm for adding two n by n matrices. So that's just you take position by position. So row 1, column 1, plus row 1, column 1 of the second matrix, and then row 1, column 2, and so forth, however you go, okay? So the basic operation there is the addition of those two numbers. How many times is it performed as a function of the order of the matrix, which is n, okay? It's going to be n squared, right? Because if we have a 4 by 4 matrix, okay, it's going to be of order that's a 4 by 4, 4 rows, 4 columns. It's going to have 16 elements, okay? So that's how we get the squared for how many times it's performed once for every element of one of the two arrays, okay? The next part asks as a function of the total number of elements in the input matrices, okay? So this one, you have to look at the total number of elements in both, okay? So I'm going to call that m. So m is equal to 2 times n squared. Matrix 1 has n squared items, matrix 2 has n squared items. Both of them have 2 n squared items, okay? So then to put that in terms of m, we just do m divided by 2, which gives us the n squared, which we know is the number of operations that we have, okay? So that's what that's doing, okay? So 4a talks about the gloves. So there are 22 gloves in the drawer, and it breaks them down. We don't really care about that, but you select 2 gloves in the dark, and you can check them only after a selection has been made, okay? So the question is, what's the smallest number of gloves you need to select to have at least one matching pair in the best case? Well, if you pick one red glove and right-handed red glove and another left-handed red glove, well, you're good. You got a pair, right? Okay, and 2 is what you need to get, okay? The worst case scenario, okay, so there are 22 gloves. If you're particularly unlucky, you can go through and pull 11 left-handed gloves, let's say, before you hit the right one at 12. So at 12, you know that you're guaranteed to have a pair, okay, of left and right, okay? Okay, so the missing sock one, again, you've got 5 distinct pairs of socks. You discover that 2 socks are missing, okay? There are only 2 possible outcomes here. There's not really an average case unless you do it mathematically, okay? Either the 2 that are lost are both going to be from the same pair, which you have 4 pairs left, that's the best case, or they're not from the same pair, which you only have 3 left. So 3 or 4 are the 2 options, okay? So the way to do this is back to what we were doing in discrete math. I mean, you can just count them, and we'll talk about that a little bit, but if you just do a 10, choose 2, and not discrete, was it called discrete? Finite math? I think they're more or less the same thing. I think it's called discrete math, though. So that's wrong in the notes. But anyway, so if you don't remember that formula, you can certainly look it up, but you can also just reason it out by saying that the first time you pick, you have 10 choices. The second time you pick, you only have 9 choices. So there are 90 options, okay? But since picking a red and a blue is like picking a blue and a red, we can eliminate half of those till we get to 45, okay? So, and 10 choose 2 is also 45. So if you have, since there are 5 pairs of socks, the best case can happen for all 5 of those pairs. So out of the 45 things that you can do, okay, 45 possible outcomes, 5 of them are what you want. So 5 of 45 is 1/9 or about 11%, okay? So that means all the others are the worst case scenario. That's 40 out of 45, 8 out of 9, or about 89%, okay? So, and then the average I didn't put on there, the average would be, the average not really useful. There's not really an average. Seems like the book answer said 3.5, and I'm not sure I actually buy that. You have to think of how many times it could be one or the other. So I don't find that particularly useful. Okay, so on to section 2.2. So with this one, you have to remember that the big O means it's the same or lower. The big theta is the same or higher, and big big omega is the same or higher, and big theta is exactly the same, okay? So when we're looking at what's on the left side of these element of, they're all the same. They're all this n times n plus 1 divided by 2. Okay. So to work that out, first thing you have to do, you take the n, multiply that out, you get n squared plus 2, all that over n, or sorry, n squared plus 2, all that over 2. And when we're doing these cases, all we care about is the highest order of n. So that's an n squared or quadratic. That table on page 59 will tell you that. Okay. So the first question then becomes, is n squared, since we're looking for big O of n cubed, is it better than or equal to n cubed? It is, so that one's true. The next one, is n squared better or equal to n squared? Well, yeah, it's equal. Okay, so that's true. The third one, is n squared in the big theta of n cubed? Okay, and I've got an error there. That should be an n cubed because that's an n cubed there. Anyway, no, so that's false. And this one is n squared worse than or equal to n? And yes, it is worse than n. Okay, so you got that. This next one is interesting. And a lot of the problems that we have that are like this, I'm not sure that I don't, so let me put it this way. I don't expect you necessarily to find the best answer. I want you to think about it. You're going to get credit for thinking about it. And I was thinking of a way that had 3 weighings that was way too complicated. So then I looked in the answer guide and found that there's a better way that I always forget that you can do. So let's follow through the reasoning on this one here. Okay. So you start by taking 1 coin if n's odd and 2 coins if n is even. Okay. You then divide the remaining even number of coins. So we know we're going to have an even when we do that. Okay. Into 2 equal size groups. Okay. So if we had 5 coins, we now have 2 and 2. If we had 6 coins, we now still have 2 and 2. Okay. So with those 2 evenly numbered coins, the 2 equal size groups, you put them for our first weighing. Okay. So one of 2 things happens. Okay. If they weigh the same, then we know all the coins are genuine and the fake coins among the either 1 or 2 that you set aside. Okay. So we can then test that to see. Okay. If the former weighs less, okay, then the fake coin's lighter. If not, it's heavier. Okay. So if the first weighing doesn't result in a balance, you're going to take the lighter group. Okay. And if the number of the coins in it is odd, we're going to add 1 to it from the coins that you originally set aside, which have to be genuine because you know that one of these is lighter or heavier. Okay. So you're going to divide all these coins into 2 equal size groups and weigh them. They weigh the same. All these coins are genuine, and therefore the fake coin's heavier. Otherwise, they contain the fake, which is lighter. Okay. So that's how that works out. And again, I didn't necessarily expect you to get that, but it's out there for you to take a look at. Okay. Section 2.3, computing the sums. Okay. And again, there are a lot of ways you could have done this. If you hard coded it into a program, it's okay. But the easier way here is to try to turn these into one of the formulas in the back of the book. Okay. So in this case, we look at this problem. Okay. Is the odd numbers up to 99, 999. So I can represent the odd numbers as 2 times I. Okay. So this is I equals 1 to 500 of 2I. Okay. I don't know why there's an equals 1 there. There shouldn't be. So that's wrong. I guess my equation editor got crazy. Okay, so we can take from that, okay, we can get the 2I part out. It's 2I plus 1. That's what that should be. No, 2I minus 1. Because it's 1 first. Yes. So 2 times 1 is 2 minus 1. Yeah, that should be a minus. That's where we're at. That's why it's there. So we're breaking these into pieces, which you can do that by the rules of summations. So we've got the 2I is one summation. We've got the 1, which is summation. Okay. This 2I is one of the formulas in the back. It's 500 times 501 divided by 2. Okay. Again, we're pulling the 2 out of that. The sum of I is whatever the value here is, 500 times 501. So n times n plus 1 over 2. Pull the 2 out. Okay. times the sum of 500 ones is 500. Okay, when you do all that, you get to 250,000. Okay, in a similar way, this is the sum of the squares to 2 to the I, okay, from 1 to 10. Okay, so we're going to break this out to this formula. Note that the formula in the book starts I at 0. Okay, so that first I we have to subtract out. So this gets us to the 2 to the I minus 1. Okay, so this summation goes to 2 to the 11th minus 1 minus 1. The minus 1 was already there. We have to subtract one more 1 because we're moving this from a 1 to a 0. Okay, which gets us 2046. Okay. So on 4A, the mystery algorithm. What does the algorithm compute? Okay, it's going to compute the sum of squares. Okay, so we get that. The basic operations multiplication, and how many times it gets executed is going to be n. And what's the efficiency then is theta of n. And then it asks if this is the most efficient way. Okay, so the answer there is a little muddy. It turns out there's a formula that you can use that can just do it right off no matter what the n is, but that's kind of esoteric. The way I like to think of it, that n sounds like not a bad thing to do because we kind of have to add every one, okay, unless we find some trick of math, okay? So that's kind of the answer to that E that got left off there for some reason, okay? Section 2.6 problem 1, that's a little bit of a tricky answer, okay, in that if we're counting the number of comparisons, there's one comparison that it doesn't count, and that's it doesn't count the A sub j is greater than V. When that first comparison fails, since it's an and, the whole thing falls apart. Okay, so we can put this, if j is greater than or equal to 0, count gets count plus 1. If we can add that after the while statement, that's going to account for that 1. And that's a fairly esoteric thing to have going on. Okay. So that's it for an explanation. If you have any more questions, make sure you let me know.